Hello, welcome back. Let's get into the third page of 2.1 here. First, we have this theorem, theorem 2.3, that you are going to prove for homework that basically says you have a distributive rule. You can distribute matrix by vector multiplication over vector addition. And this looks nice. Like if we're going to do like algebra treating matrices as objects, it sure would be nice to have a distributive rule. So it's nice that this works out, but it's not totally obvious that it should work out because remember, this notation is hiding a lot of complexity. Each one of these things is like a linear combination of the columns of A. So it turns out it does work out, and you can prove it. But also notice we have this sort of associative rule. If you scale a vector by k first and then multiply it by a, you get the same thing as if you multiply the vector x by a first and then scale it by k. So all that is stuff that is going to make doing algebra with matrices as the objects work nicely. Now, let's look at this definition of a linear transformation. So remember, the section was called linear transformations. So far, we were just talking about transformations in general. But what it means for a transformation to be linear is that it satisfies these properties. And these are the same basic properties you were looking at in the warm-up exercises. You were showing that f of x, which is 5x plus 1, is actually not a linear function because it fails these. You get different things for some values of x and k and z here. So you'll notice that this is saying exactly the same thing as this theorem is. It's just that we now have, instead of a, we're just writing that as t here. So what we just showed is that any transformation where the definition of the function is you just multiply the input by x like this, that is a linear transformation. And we're going to soon see that all linear transformations are of this form. This is kind of like in section 1.5, I think it was, about subspaces, that every subspace of RC can be written as the span of some vectors in RC, and the span of some vectors in RC is a subspace, but they're different ways of looking at the same thing. Here, we're going to show that linear transformations, and linear transformations means functions that satisfy these two properties, are the same thing as matrix transformations. That can be written t of x equals ax. So let's look at example 6. We covered back in 1.5 that if you're given any two vectors u, think of u as the arrow that points there or just as the point, u and v we're thinking of as an arrow, the set of vectors that can be written like this is the set of all points on this line that goes through the point u, but the line is parallel to the vector v as an arrow. Okay, so any line can of course be written like that because no matter like what line you have, like there's always going to be some point on it you can call u and just take any vector parallel to it and call that v. So we're going to explain why linear transformations map lines onto lines. And what do we mean by that? Well, let's say you have some u and v, and we want to think of what happens when you input a point like that into a linear transformation t. The transformation here is big T. Let's call that a linear transformation. And I want to talk about the set of points you get like this, where t, little t, can be any real number in R. So what is the set of outputs that corresponds to input points that are all on the same line given some u and v vectors? Well, because t is a linear transformation, it has the distributive property that goes with it, property 1. So we can say this vector is the same as big T of u plus big T of little t times v, such that t is any real number. And we can also take out the little t, because that's just a real number that we're scaling the input vector by. So you can just take that scalar out. And what do we get? Well, these output points are the set of vectors you can write as t of u plus any scalar multiple times big T of v. Now maybe the output is actually in R3 or something different. I don't know. But wherever it is, like t of u is going to be some vector, which we're going to think of as a point. And then t of v is also a vector. Maybe it looks like this. And we're going to think of that as an arrow. We know we can take any scalar multiple of that and add it to t of u. And of course, the little t could be a negative number, so you can go off in this direction. So all of these points together, what you get is the line through big T of u parallel to big T of v. So that's what we mean when we say linear transformations map lines onto lines. Let's look at another example here. Here we have I is the 3 by 3 identity matrix, where the columns are E1, E2, and E3, also known as I, J, and K if you prefer. So if T of X is defined as the identity matrix times X, let's find T of 9, 8, 7. Again, writing the point 9, 8, 7, that's just alternate notation for the vector 9, 8, 7. And so this just means 9 times E1 plus 8 times E2 plus 7 times E3. And it all comes out to be 9, 8, 7. So in general, it turns out that T of X is just equal to X here. That I times X with this matrix I does not change X. That's why it's called the identity matrix, because the output is identical to the input. You could say like the function just identifies what the input is, and the matrix sort of functions like the number 1. Like if we just had a regular old real valued function, you could say this is the same as like f of x equals the number 1 times x. So the identity matrix works kind of like the number 1 here. Okay, that's a good point to take a little break. We'll split up this section into more smaller videos. In the next one, we'll look at a more complicated example.